Hello everyone. So today we'll be solving the problem traveling graph, right? So this was asked in the Codeforces Alpha round 21, which is in the Codeforces format. This is fine. Yeah, now we can just go through the question. It's very easy to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So just give me a second here. Yeah. So we are given an undirected weighted graph. Yeah. So we have been given undirected weighted graph with the possible loops and multiple edges. Yeah. Possible loops they have mentioned and multiple edges. And one more thing, it is undirected weighted graph. And what we need to do here, we have to find the minimal length of a cycle that starts at vertex 1. Yeah, minimal, this one. We need to find minimal, what do we call this one? We have to find the minimum length of the cycle or minimal length of the cycle that is starting at the vertex 1, that is starting at the vertex 1 and traverse every edge at least once and traverse every edge at least once, right? And traverse every edge at least once. Yeah. So we have to return -1 if it is impossible. We have to return -1 if it is impossible. And remember one thing, n, we have been given n less than or equal to 15. You can clearly see here within the constraints. And m less than or equal to 2000, right? M less than or equal to 2k or 2000 here. Yeah. This is fine. So let me read the question loud. Just listen to this. So we are given an undirected weighted graph with a possible loops and multiple edges. We have all we need to find here as we have to find the minimum length of the cycle. This one minimal length of the cycle that starts at vertex 1. That starts at vertex 1 and traverses every edge at least once and traverses every edge at least once. We have to return -1 if it is impossible, right? N is less than or equal to 15 and M is less than or equal to 1000, right? So this part. Yeah, I hope this part is completely clear, man. This is fine. Yep. Now, yep. Now, as we are completely familiar with the question, let's move on with the input output part, man. So here we have been given 3, 3, right? So 1 second. Yeah, 3, 3. So we have been given this one. What do we call? N and M, and we have been given here just as well, right? 1, 2, 2, 3, as well as the 3, 1. Yeah, now let's discuss the approach. Let's discuss the approach. Same thing goes for the example 2 as well, right? So let's consider the first example here for the this one approach, right? So let's discuss the approach. You'll come to know, man. Yeah. First thing is we will be making use of the Chinese postman. This one Chinese postman to solve this particular problem, right? So first step here would be, so let's just listen to this carefully. So here sum of all the original edges that we'll be considering here. Sum of all the original edges, nothing but the last one here, 1, 1, 1 they have given, right? Sum of all the original edges would be first thing, it will be equivalent to the 3. It will be equivalent to the 3. So this one is first step. So we will be going with sum of all the original edge weights actually, right? Yeah, not the edge, sorry, edge weights actually. These are the edges, right? 1, 2, 2, 3 as well as the 3, 1 is edge. So this is nothing but the last one is nothing but weight. So I don't get confused here. Simple one, right? So here sum of all the original edge weights, 1 plus 1 plus 1. So the last number in every line, that is nothing but the weight. And the first two numbers are edges. We know that. Yeah. This is equal to 3. Now this is the base cost because every edge must be traversed at least once. Every edge has to be traversed at least once. So what this is actually, this is the base cost. Just remember this one. Let's move on with the second point, man. This is simple. Now we need to count the degrees. When I say we need to count the degrees, so 1, 2, 3. So let me draw the graph for this. Just give me a second here. Also, let me draw this one graph. So this will be one undirected graph, right? So 1 to 2, 2 to 3. So we understand this one clearly, 2 to 3 as well as 3 to 1. So this is the graph actually, right? 1 to 2, we have the value 1 and 2 to 3, we have the value 1 and 3 to 1 also we have the value 1 here, right? So this is the graph that this is the input that we are considering. So this is the graph actually. Yeah. So we are considering this input basically. This is the graph. So as I have said, first the sum of all the original edge weight. So this last one is nothing but weight, right? So weights actually this 1, 2, 2, 3 as one, this one 3, 1. these are the edges. The last number is nothing but the weight. So this is nothing but n and m, right? So number of this one, what do we call? You can consider number of nodes here. 1 2 3, we have three nodes, n, and 3 is nothing but the number of weights here, 3, right? So this is fine, man. Now yeah, as I've said, we are going with the sum of all the original edge weights, nothing but here in this case 1 plus 1 plus 1, all the original weight adjustments, this value 1 plus 1 plus 1, 1 to 2, 2 to 3, and 1 to 3. Yeah, this is fine. So this is considered as I've said earlier, this is considered as base cost, right? So this is fine. Let's move on with the second point here. Now we will be counting the degrees actually. Vertices 1 2 3 all have degree 2. See here, 1 to 2, 1 to 3, degree 2, 2 to 3, 2 to 1, degree 1, as it is undirected graph, right? So 3 to 1 and 3 to 2. So this is also having degree 2. All the three vertices are having this one, degree 2. So all 1, 2, and 3 vertex is having degree 2. That is nothing but even. There are no odd degree vertices to pair here. There are no odd degree vertices to pair here. So you can notice one thing, we are going with the Chinese postman. So this can be solved by Euler tour as well. Yeah. So because see here, uh, all this one, there are no odd degrees, and this one, we have the degree even here. We can just go with a Euler circuit, right? This one, right? Circuit. So that one also we would have made use of. So this is one, this is fine, man. We'll be going with this one. What do we call? Chinese postman. So this is fine. There are no odd this one. There are no odd degree vertices to pair here, right? So total initially what we will do, we'll consider total equals 0 initially, as we don't have any odd degrees to pair actually. Yeah, total I have just written here TOT, right? So next let's move on with the third step here. Nothing but if every vertex has incident edges, right? If every vertex 1 2 3 is the vertex that we have, if every vertex has the incident edges that is reachable from vertex 1, in this case it is true, right? So here, if every vertex has the incident edges that is reachable from vertex 1, see, 2 is reachable from 1 actually, 3 is reachable from 1. Yeah, the same thing for every vertex that has incident edge that is reachable from vertex 1. In this case, for our example, whatever the example that we have considered, it is true for our example, right? So we don't need extra shortest path pairings for this particular input. We don't need any extra this one, shortest path pairing, actually extra shortest path pairing, right? Yeah, this is fine. Now let's go with the Chinese postman result. Yeah, let's go with the Chinese postman result, right? So this one will be equivalent to the sum of all the edges, right? Sum of all the edges, I'll just write here SE, nothing but sum of all the edges plus minimum pairing cost for odd edge vertices, minimum pairing cost for all the edges, this one odd vertices, right? So this one, minimum pairing cost for odd degree vertices is 0 in our case, right? So I'll just give here odd odd degree vertices, right? So odd ODV I'll give here minimum this one pairing cost for odd degree vertices. In our case, we have even vertices, right? So this one, sum of all the edges, we have got 3 here, all the edge weights, right? Sum of all the edges is 3, and the minimum pair cost for odd degree vertices, we don't have any odd degree vertices vertex for this particular this one input or the example. So we will be going with 3 plus 3 plus 0 is nothing but which is equivalent to the 3. So output that we got here is 3, right? So if you have odd degree vertices, then we have to go with the minimal pairing cost of the odd degree vertices as well, or of the odd degree vertex, right? So this is fine. Now the output that we got here is 3, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So now as yeah, the output that we got here is 3, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So our approach works absolutely correct here. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to big of n cube here. So we can just write it in this way, big of n cube plus m plus 2 to the power of t into t square into t square. So where n is less than or equal to 14 accordingly with the constraint, right? For the Floyd-Warshall, right? And also for the Floyd-Warshall, it will be n cube basically. In simple terms, it will be n cube. So we know the Floyd-Warshall algo. We have already discussed. We had discussed the Floyd-Warshall algorithm very recently, right? So here we are considering m, this one, n plus m. So this is for the Freud partial. We'll be going with the Freud partial, man. We'll be making use of the Freud partial. Just remember this to write the code. So m, this m is for reading the edges. This m is for reading the edges, and t is nothing but it is equivalent to the number of odd degree vertices. It is number of odd degree vertices, right? So I hope this is fine, man. Yeah. Now here dominant term is Floyd actually, big of n cube, and dp of big of 2 to the power of t into t square. Just remember this. Yeah. So overall time complexity, we can just represent this one in this way. Yeah. Now what will be the space complexity? The space complexity would lead to big of, I can just write it in this way, big of n square plus 2 to the power of t. Right. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n cube plus m plus 2 to the power of t into t square, and big of n square plus 2 to the power of t respectively, right? Space complexity is big of n square plus 2 to the power of t for the distance matrix, as we'll be considering the distance matrix as well as the dp array, right? So this you'll get to know when once we write the code. So yeah, I just wanted to discuss this one. So this is the complexities part. Now as we are completely familiar with the complexities as well as the approach, we are good to write the code. Let's start writing the, right? So first we'll be making use of this one, what do we call, fast input output and utilities, right? So for that one, let's import input output package. Along with the input output package, let me import utilities package as well. Yeah, this is fine. Now let's go with the class. We have to make use of the class as usual. So I'll just go with the class main. So within this class, let's do one thing. Let's go with this one, vertices, edges, and also the total, right? So we have to initialize vertices, nothing but m, edges, nothing but m, and the total. Total is nothing but count of odd degree vertices. So I'll just go with here. Sorry, here static int n comma m. This one total. Let me initialize this one to 0. Next, let's go with the distance. This one variable, nothing but it is the shortest distance between I and j. Let's initialize that one. So I'll just go with static here. This one int, this is fine. Distance equals. So this one will be new int of this one. What do we call, 20 as well as the 20. Right. So this is fine. 2020. Right. So now let me go with uh, int as well. Just consider variable in. Let me assign this one to new int of 20 again. So this is fine. Also odd degree vertex we need to consider. So this one odd, new int of again 20. So this is also fine. And also we have to go with the, we will be making use of the DP, dynamic programming, right? So I'll just go with DP equals. Let me initialize this one to the new int of uh, 1 left shift by 13. So by 13, or let's go with the 15. What if 13 doesn't work? Let's consider some extra, right? In of I is nothing but the degree of the vertex I, this one in, and odd is nothing but here this one, list of the vertices with the odd degree. As we know, as we have discussed this one in the approach, dp is nothing but the, here we'll be going with a bit mask here, right? So bit mask along with a dp, actually dp mask, dp of mask is nothing but minimal extra cost to pair the odd vertices on the mask, right? So next thing, so let me go with here static, static here final int. So let me go with infinity equals, so I'll just go with this particular, this one, what do we call value? I'll just go with 0x3f followed by uh, 3f thrice, actually 4 times totally, right? So this will be 3f, 3f. This is fine. Yep. Now this is just for the what, infinity value for the initialization. Yeah. So this is fine, man. Now let's go with the main method. Now let's go with the main method. Let me remove this one and let me give here this one, throws exception. I'll just go with throws exception. Right. So this is fine. So within the main method, Now let's go with the fast input, fast output, as well as we have to read the first line. For the fast input, we'll be going with the buffered reader. For the fast output, we'll be going with the print writer. And for the reading the first line, we'll be making use of the token string tokenizer. And also we have to read the number of vertices as well as the number of edges, nothing but n and m. This is purely related to the this one. What do we call input output? Let me copy paste that one. Just give me a second here. So I'll just come here. Let me paste this one. Yeah. As I've said, fast input, buffered reader, fast output, print writer, string tokenizer, as we need to read the first line, and we are this one parsing this one n and m, right? The first line, this one, n and m, integers 3 and 3. So this is fine, I believe. So the next part would be, so we have to initialize all the distances to the infinity. Let's move on with the iteration part. So this one will be for int row actually of distance. This is fine. Arrays dot fill, arrays dot fill of row, comma infinity. This is fine. Yeah, we are just initializing all the distances to the infinity. Now let me initialize sum to 0. Let's do one thing now. Let's read the edges and update the distance in as well as the sum in variable that we have considered, as well as the distance dis variable and sum, right? So this is fine. Let's move on with the for loop. So this one will be int I equals 0, I less than m. So let me increment I. So within the for loop, let me go with the string tokenizer, new string tokenizer. This is fine. Buffered reader dot read line. So this is also fine. The next part would be, let me go with int u equals integer dot parseInt. So this is fine. I'll just go with string tokenizer dot next token. Uh, this is fine. So this is nothing but the edge start. So we will be going with a this one Floyd Warshall along with the this one. So very recently we have discussed the Floyd Warshall algorithm where we have got the opportunity to implement here, right? So let's implement. So this is fine. This is we have to consider edge start, edge end, as well as the weight that they have given here. This one, fine. This one. So Floyd Warshall is comparatively faster compared to the Millman Ford, right? So that is the reason I just wanted to go with the Floyd Warshall. So this is fine, I believe. Now let me copy the same thing. Edge start. We have to go with the edge end, nothing but V. Also, we have to go with the weight, nothing but W. So let me change this one to V, and also let me change this one to W, right? So this remains same. String tokenizer dot next token. These things we are just passing, right? So these values, this is fine within the input. Now let's add the weight to the total sum, right? So that's what we did. So this one will be simple, man. Sum equals sum plus weight. Yep. Now let's go with distance of u v equals distance of this one v and u. This is fine. Distance of vu that is equivalent to math dot mun of distance of u v comma w. So this is fine. Okay, w, right? So now what shall we do? Let's store the minimal direct edge between u and v, right? So we have to increment the degree. So this one will be in of u plus plus, also in of this one v plus plus. We're just incrementing the degrees here. This is fine, man. Now let me come out of this one entirely. Let's go with a Floyd Warshall for all the pairs shortest paths, right? The same thing, 3 for loops, implementing the algorithm. So let me type this one. Just give me a second, man. Here, for let me write this one quickly. For k equals 1, so this one has to be k less than or equal to n. K plus plus. So this is fine. So let me not make use of this one. What do we call that one? Flower places setup. So this one will be for I equals 1, I less than or equal to n. Yeah. Next for loop is for int. So we have to consider j, right? Int j equals 1. N m and so here we are considering only n, right? So this one has to be I less than or equal to n, remove the single inverted comma. So this one will be, what is this? J plus plus. Yep. Now within the for loop, let me go with distance of ij, and a formula thing, right? So this one will be math dot min of. So I'll just go with distance of I and distance of j, comma distance of I and k, also distance of kj, right? So here we have to, yeah, distance of ik plus distance of jk or kj. So let me go with the kj here. This is fine. Yep. Now let's do one thing. Now what we need to do here, we have to check if every vertex with the edge is reachable from the vertex 1 or not. Let's go with a simple for loop for this. So this one has to be for int I equals 1, I less than or equal to n. So this one will be I plus plus. So if this one in of I, this is fine, where if it is not equal to 0, and this one instance of this one, what do we call 1, so this one will be I, if it is greater than 1e9, 10 to the power of 9 actually, so then what we will do, so it's impossible to traverse all the edges, right? In that case we have to print -1, as they have given the same thing, as they have asked us to do the same thing within the question actually. Yeah, so I'll just go with here println. So this one will be -1. This is fine. The next step would be out dot flush. So this is fine as well. The next step would be, let me give return man. Yeah, this is fine. So I'll just come out of this one entirely. Now let's collect all the odd degree vertices. When I say let's collect all the odd degree vertices, let me go with a for loop here. Int I equals 1, I less than or equal to n, I plus plus. So this is fine. And if here, so this one degree of I, so this one modulo 2, the remainder is 1, then let me go with odd of. So we have to increment total. I'll just give dot here. This is fine. So this has to be within the, yeah, this is fine. This is within the square bracket itself. So let me assign this one to the I. Yep. Now let me go with arrays dot fill. Let's fill the dp initially with the infinity. Infinity INF. Yeah, this is fine. Now what we need to do, we have to go with the base case. Base case nothing but no add vertices to pair the cost 0. So this one will be dp of 0. Let me assign this one to the 0. Now let's do one thing. Let's go with a for loop man. For loops basically. So we have to go with the dp over subsets of the odd vertices. Why? To find the minimum cost to make all the degrees even, right? So that's what. So let's go with again 3 for loops. So here, so this one will be I equals 1. So I less than, I'll just give here 1 left shift total. Actually, this is fancy way of writing. Don't worry. So I plus plus, this is fine. So within this for loop, let's do one thing. Let's only consider even size subsets first. So let me go with a simple if condition. So this one will be integer dot, let me consider bit count here. Integer dot bit count of I, bit count of I. So modulo 2, if it is equivalent to 1, then let me give continue. Let me give continue here. This is also fine, right? So we are just only considering even size subsets here. So let me go with one more for loop here. So this one will be for int j equals 1, j less than or equal to 12. So this is fine. Let me increment the j. Now let me write the simple if condition here. So this is I right shift. So this one j minus 1, this is also fine. Let me come out of this one entirely. Uh, Bitwise and 1. So this one, if it is equal to 0, if it is equal to 0, then let me give continue here. Nothing but we are skipping if jth vertex not in the subset, right? So this is fine, man. Yeah. Now let's do one thing. Let's go with one more for loop here. So this one will be for k equals j plus 1. This is fine. K less than or equal to. So this is also fine. Finally, k plus plus. Let's increment the k. So within this for loop, so we have to skip if kth vertex is not present in the subset, right? So I'll just go with here the similar thing to the previous one. So I'll just go with I, right shift k minus 1. This is fine. K minus 1 bitwise and 1 here. So if it is equal to 0, then we have to skip. I'll just give the continue keyword. This is fancy way of writing. If you just want to write it in a different way, understandable way, you can just go for it, right? So this is fine. So let me come out of this one entirely. Now we have to pair j and k. We have to remove them from the mask and we have to add the shortest path between them, actually between j and k, right? So that's what we need to do here. So how we can do that, let's see. So this one will be dp of I equal to math.mun of. So this one will be dp of I. This is fine. And dp of I, if I to the power of, so this one will be 1 left shift. So this one will be j minus 1. This is fine. J minus 1. Yeah, j minus 1. So this is XOR. We'll just go with 1 left shift here. Let me go with k minus 1. This is also fine. Yep. Plus, I'll just go with distance of here. This one. Let me go with odd here. This is fine. Odd of, let me go with j. Yep, this is fine. Again, let me go with odd of j we have considered, right? So odd of j we have considered. We have to go with the odd of k actually. Yep. So we are done with this part, man. We are done with this part. We have successfully paired j and k. In the sense, we have removed them from the mask, and finally we have added the shortest path between j and k, right? So that's what we did. Now let me come out of this entirely. So we are left with this one answer part in output part basically. Yeah, we have to go with the final answer, meaning let's go with the sum of original edges plus minimal extra cost to pair the odd vertices, right? So again, so I'll just go with output println. This one will be sum plus dp of 1 left shift total minus 1. This is fine, man. So this total dp of, so this one has to be within the parenthesis, not the square bracket. So this is fine, I believe. Yep. Minus 1, this is fine. But we need to use this one as well, right? Let me make use of the square braces here. So let me close the square braces here. This is fine, I believe. Yep. So yeah. Now let's do one thing. We have to flush the output or we have to close. I'll just go with output flush here. This is fine, man. Yeah, we are done with the code actually. We are done with the somewhere something I have done something wrong. So here, yeah, this one. I didn't see this bracket at all, I believe. So here I have to place this one here. Yeah, now this is correct. Bracket placement. This is fine. Now we are done with the coding part. So before checking the code with the different inputs or the outputs, let me copy paste the signature starter template. Just give me a second here. So I'll just come here. Let me paste this one over here. Let me come here. Let me copy this one. The output that we need to get here is 3. Let's check the same. We are getting the output 3, right? So let's check with this actually. We have to get the output 4. Let's see. Yeah, we are getting the 14. Yeah. Now let me copy this one entirely. So I'll just submit this one, paste this one and submit this one. Let's wait for some time. I hope this works for all the cases. Let's see. wait for some time. Why this is stuck at run this one? Test one. So yeah, this is showing accepted in the toast, right? See here the verdict that we got here is accepted. So whatever the code that we have written works absolutely correct for all the test cases. Yeah. Yeah. For now, this is it. Thanks for watching, guys.